Welcome to this lecture of Robotics 2 on the Newton-Euler approach for deriving dynamic models of robots. We will present this method starting from a comparison with respect to what we have seen so far, namely the energy-based approach, which is based on the Euler-Lagrange equation. So in this comparison, let us review what are the advantages of the Euler-Lagrange approach and what is its main use. Namely, we have considered the energy of the system, of the robot considered as a whole entire system of multi-body. So summing up potential energy and kinetic energy of each body and then building the Lagrangian and applying the equation. Now, in doing this, we end up with a model which relates motion to applied external forces. There is no information at all on what happened between forces exchanged between body while moving or while standing in a static situation. Because these internal forces are never generated because, remember, on the right-hand side of the equation, we put forces only performing work on the generalized coordinate. So since the internal constraint forces which connect one body to the next one through the joints are never produced, so they are eliminated from the picture. This is important for what we will see next on the Newton-Euler method. We end up with a so-called closed form equation expressed in possibly long symbolic terms which complete in one shot at the end the dynamic description. Now, apart from detailing the single expression of the dynamic terms, the general structure that we obtain from the Euler-Lagrange approach allows us to study some generic properties of the robot. For instance, we have seen as a first and basic property that the inertia matrix is always a positive definite symmetric matrix, and therefore it can always be inverted. And this is the reason why we can safely perform simulation of our model, so solving the direct dynamics, because we need to invert there the inertia matrix, and this is never singular. Moreover, we have investigated some internal structural properties. For instance, the fact that if you factorize properly the quadratic terms of the Coriolis and centrifugal forces, quadratic in the velocities, with a suitable matrix S, which can be computed from the Christoffel symbols, then this fancy property of m dot, so the derivative of the inertia matrix minus 2s, is a skew-symmetric matrix. We will use this later in control design. Similarly, we have, from conservation of energy, we have seen that m dot minus 2s for any factorization matrix S of the Coriolis and centrifugal term will vanish when put in a quadratic form where the external vector is the same q dot which appear in the internal matrices. This is another fundamental property from physics that will be used, for instance, for proving that a very simple PD control allows global stabilization of any desired equilibrium state in the absence of gravity, one of the first basic control results that we will see later on. So this model is very useful for analysis and also for, let's say, designing and sizing the components, because we have explicitly masses, inertias, center of masses present. So from a mechanical design, if we want to start from scratch, we could establish the contribution of each terms in a very clear way. However, there are other things that this approach it's not suited for. I mean, you can use it also for other purposes, but it's not fully suited. And this is why the Newton-Euler method in our approach comes into play and becomes a very useful additional tool. So Newton-Euler method, as we already introduced, is based on balances of forces and torques. Newton equation for a single mass m is just F equal m times the acceleration. If I had a body in pure rotation around one of its axes, I could write a similar equation in terms of angular quantity. So inertia times angular acceleration equal torque. In this sense, this could be named the Euler part of the Newton-Euler equation, but this would underestimate the contribution of Euler to the picture. Anyway, we balance forces and torques with their effect. And we do this for each couple of connecting links. So link I with link I plus 1, and so on, from the base to the tip. So we write several dynamic equations that balances forces and torques. And then we can combine all them together and, in fact, substitute quantities from one equation to the other, using also the fact that in this equation acceleration comes out together with angular velocity. We will see this in detail. And all these quantities can be computed, again, in a recursive way, using the moving frame idea, much the same way in which we computed omega I and VI and then VCI, so the velocity of the center of masses, with the moving frame formalism in the efficient implementation of the computation of kinetic energy. Now we move one differential step up those type of relationship. And to say the truth, the moving frame concept was originally introduced exactly for the Newton-Euler method, and we have downgraded it later for the recursion on velocities for the kinetic energy computation. So when you do all the computation and substitute all these quantities symbolically, you end up with equations which are exactly the same as the Euler-Lagrange approach. In fact, the system is the same, the assumptions are the same, rigid bodies connected by rigid joint of the revolute or the prismatic type, so we should end up with the same equation. But this is really very boring to be done because those equations are best for numerical evaluation. So instead of replacing symbolic terms from one equation to the other, we just plug in the numbers depending on what we need to do. For instance, the most classical situation is using Newton-Euler method for inverse dynamic computation. In that case, we assume that a trajectory, desired trajectory, is given, and we would like to compute the torque that produced that motion. So we plug in those numbers for any instant of time, so q at time t, q dot at time t, q double dot at time t. We make the recursion from the kinematical point of view. We compute numbers in terms of omega, omega dot, and whatever kinematic quantities we need. We plug in those into the balance of forces and torques equation, and we evaluate this again numerically. So at the end, we have a numerical value of the torque needed to do the motion. So we never create long symbolic terms to be evaluated, although the two methods are, in fact, equivalent. There's another aspect which is important, other two aspects. So because we do this in an efficient way, every time we need to evaluate model-based control law, so control law that uses the information on the dynamic model of the robot, we will synthesize this control law, although we may have designed them looking at the Euler-Lagrange equation. Once we realize what we need from the model, we compute those terms, or all terms, using the Newton-Euler inverse dynamics, or a set of this equation. We will see this in the detail later in today's lecture. And this is one aspect. So good for synthesis as opposed to good for analysis here. The last point, which is buried inside this last comment, this last bullet, is that in fact we generate something more than just the forces needed to reproduce that motion. Because in every passage from one link to the other, we also have internal forces being computed numerically. And then we discard those that do not produce motion to retain only the numerical values of torques, which are responsible for joint motion of the entire structure. So we have an extra computation, extra quantities being generated, as opposed to the Lagrange method, which discards simply all forces that do not produce motion, so all internal forces due to the constraint of the structure. For instance, those internal forces may be used to evaluate what is the stress in doing a motion for a given robot once you assign numerical values to the dynamic parameters, masses, inertia, and so on, and you generate a motion. This motion can be done easily, but the internal stress may be excessive for the material that you're using. So this is also a good tool for mechanical design. Okay, so with this in mind, I think it's familiar to everybody that we have to move to the acceleration because this is the nature of the Newton equation of motion. And since we will deal with a moving frame formally, so we will have vectors that are recursively defined in local frame, which are moving because the previous joints are moving as well. Let's do this basic computation, which gives an expression of a time derivative of a generic vector, whatever, not necessarily a velocity, which is expressed in a moving frame. This vector may change its length or may be a constant vector. But since, even if it's constant, because it is expressed in a frame that is moving with respect to the, let's say, reference zero frame, so with respect to an inertial frame, then it will change direction. So if we represent the endpoint of this vector and its velocity, even if the length of the vector is not changing, this endpoint is having a velocity because of the moving frames. Okay? So we will have two contributions, in fact, when we take the time derivative, the fact that a generic vector may change its length and the fact that the vector changes its orientation. Okay? How do we deal with this? So let's start with a vector which I call v. It could be a velocity, if you wish. And this vector related to some link or frame, we just reason with frame I, so a point in frame I which is moving, is expressed in frame 0. So we use the standard notation with a subscript and a superscript. So the 0 in superscript means that we are expressing this vector in frame 0, but the subscript I tells us about the body that we are considering or the frame we are considering. Of course, we could have the expression of the same vector in frame I, and the relation is through the rotation matrices R0I. Okay, this is quite standard. Now let's take the time derivative of this vector. So on the left-hand side, we will have vi dot 0, and this is, let's say, if v was an velocity, this is an acceleration expressed in frame 0. So let's baptize this ai in frame 0. And of course, also this vector can be expressed in frame I, so we can write the relation ai of 0 equal to the rotation matrix 0i times the vector ai expressed in frame I. So this is on the left-hand side. Now on the right-hand side, so we take the derivative of R0I VII. This is a product, so we take the derivative of one term and times the other not differentiated and vice versa. So we have R0I times VII dot, and then the derivative, the time derivative of the rotation matrix times VII. Now we use one basic property that we have found in Robotics 1 while dealing with variation in time of rotation, so their time derivative. This can be expressed as the skew-symmetric, as the product of a skew-symmetric matrix S, which is composed with the angular velocity associated to the rotation matrix. So this is a rotation matrix from 0 to I. So this angular velocity will be omega I expressed in frame 0 times the same rotation vector, rotation matrix. So we replace this in this way. And now we recognize that the product of R0I times VII is a vector, and here is the vector. And if we have a product of a skew-symmetric matrix times a vector, this is equivalent to the cross product of the vector inside the skew-symmetric matrix times the vector outside. So we have reversed this notation because this is the nice way to write things. Now, we can recognize here that this is an angular velocity of body I or frame I expressed in frame 0. Again, we can introduce the rotation matrix R0I and express this in frame I. So we substitute this R0I times omega II. And then we have this rotation matrix in front of all the terms. So we factorize this out. And this is the final result. So R0I times a vector which is VII dot, but not only, also omega II times vector cross product of VII. And you see that while this has the dimension of an acceleration, if v was the velocity, these are the product of two velocities, so quadratic product. And we recognize this again, the generation of Coriolis forces and things like that. So now if you compare this expression with this expression, we have a non-singular rotation matrix in front, so we can eliminate this and write that the derivative, remember, of a vector expressed in a moving frame is the derivative of that vector, if it changes intensity, times this cross product. So this is a basic relation that we will use later on. There's a special case. Suppose that you have a unit vector EI in place of VI. So this is a unit vector, so its intensity does not change, but it belongs to a frame that is rotating. So let's take this vector EI. This length will not change, so EI dot expressed in I will be 0. So this part will be 0. And now the whole frame is rotating, so this vector is rotating as well around an axis, and this axis is where the angular velocity omega I is defined. So this endpoint will have a linear velocity. So this will be the derivative of AI in time, not because it changes size, but it changes direction. And this velocity will be exactly the vector product of omega I vector EI. And it will be oriented, it will normal to both vector as the property of a cross product. If you do the cross product of two vectors, you get a vector which is orthogonal to both components. Okay, so this is a special case when this term is 0. This is why I said that VI may be a generic vector, not necessarily the velocity, but of course I use the notation VI because we will use this mainly for velocity, but not only. So this is a basic computation. Let's put it on the side and go ahead. So let's consider now a rigid body. What is the Newton equation for a single rigid body? You look at the mass, you look at all forces acting on this mass, and Newton said that the product of the sum of all forces acting on this mass m is equal to the variation of the linear momentum. Now, written in this form, you write the sum of all forces, whatever forces. It may be a gravity force, it may be a force that the body inherits from other contacting body, like in the chain of rigid links in the manipulator. Now, the linear momentum is just the product of the mass times the velocity of this body, which is concentrated in a point, let's say the center of mass itself. Since the mass is constant, this derivative is simply m times v dot c, and now we find the usual form, mass times acceleration. Okay, but it's nice to write it in this. It's not mass times acceleration per se, it's the time variation of the linear momentum. Why this way of rephrasing the same thing is interesting? Because when we move to the angular part, so the Euler dynamic equation, the balance are among torques. So the sum of all torques applied to our rigid body is equal to the variation of the angular momentum. If mvc is the linear momentum of a concentrated mass, m, the angular momentum is the product of the inertia matrix of this body times the angular velocity of the body. So I of omega, I times omega, where I is the inertia matrix. So let's write this down explicitly, and let's see what happens. So here is our statement, exactly the dual in the angular terms of the previous one. So sum of all the torques, I call this torques mu, is equal to the time derivative of the angular momentum. Now, this is a product of two terms, so I will distribute the differentiation over the two terms. But before doing this, of course, this is true in any reference frame. For instance, in the zero reference frame. So all quantities should be expressed in the zero reference frame. So omega is expressed in zero, and the inertia matrix is not expressed in the local frame, but is expressed in the frame zero. And we know that in the local frame, the inertia matrix of a body is a constant symmetric matrix. But if now I move the body around with respect to the, or I place it in different position with respect to a zero frame, then this inertia will vary, and the rule of change is given by this product. We found this already. So R times the inertia matrix in the local frame, so a constant inertia matrix, times R transpose. So when we do the derivative here, first we take I and we take the derivative of omega, so we have an angular acceleration omega dot. And then we take the derivative of I, which is changing because of the orientation of this body, times the undifferentiated omega. Now let's do this differentiation explicitly. So we have R dot, because R may change over time, times I bar, which is constant, times R transpose. Then the second term will be the derivative of I bar, but I bar is constant, so this disappears. And finally, the third term in the derivation, R I bar R dot transpose, times omega. So now again, we have twice the derivative of a rotation matrix. Now we have learned how to substitute this. So in place of R dot, we put S of omega times R, and this is the first time here. And then here we have R dot transpose. Remember, transposition and differentiation commute, so we can take R dot and then transpose. So we get S omega times R transpose, so we exchange the order, and in place of R dot transpose, we have R transpose, S transpose omega. And then outside, again, another omega. Now, there is a simplification here, because here, on this side, I have reconstructed exactly the inertia in the, let's say, base frame. So this is S omega I inertia matrix times omega. And S omega times a vector I times omega is just the cross product of the omega inside the skew symmetric matrix times I omega, and this is the extra contribution together with the first one. Now, the last term just vanishes. Why? First of all, when you have a transpose, you know that this is a skew-symmetric matrix, so S transpose is equal to minus S, so you can bring a minus outside here if you wish, so that you find here S omega times omega, which is nothing else than the cross product of omega by itself and the cross product of two parallel vector, or the same vector itself, is just 0. So this last term vanishes. So you see that the main difference between the linear and angular part is the introduction of an extra term here, which is not present in the Newton equation, just because in the Newton equation we have a scalar mass which is invariant with respect to any reference frame, while in the angular momentum we have an inertia which changes with the reference frame. So this is why we need to introduce this extra term. Of course, if the product of the inertia of the body times the angular velocity that this body has is again parallel to omega, so this is just a scaling factor. For instance, if I is diagonal and have the same elements on the diagonal, the product I omega is just a scalar time omega. And this vector product will vanish as well. So there are cases where this term vanishes, but in general, you have it there. So the other things that we will use now, these are the basic Newton-Euler equation. On the left-hand side, we just wrote sum of all forces acting on the body, sum of all torques acting on the body. But now we will look at the generic link in the structure, and among those forces and torques, there will be also interacting forces and torques connecting this body with the previous one and with the following one through the joints in the structure. Okay? So when doing this summation, we have to use another basic principle, the principle of action and reaction, which simply says that if a body applies a force to a second body, the second body applies minus this force to the first body. So this is a reversing sign depending on which is your focus of attention. If you're looking at body I, then you would like to sum all the forces acting on body I from the previous body I minus 1 and from the following body I plus 1. But if you define F of, let's say, I as the force in one direction, then the following body will apply the negative of this force to the previous body. It will be clear later on. So this is a basic physical property that we will also use now. So let's go into this detail. So first we write the balance of forces. So we consider a generic link in the structure, any form, we don't care. This is link I. So because of the Dynamic-Tartenberg notation, this is connected to the link I minus 1 by a joint I. So we have an axis of joint I, and by the assignment of frame, we know that on this joint axis we have the Z I minus 1 axis of frame I minus 1. And at the end, or at some other place of the body, we have the connection with the next link, so link I plus 1. So there will be a joint axis I plus 1 with, on top of it, the direction of Zi, the frame, the Z-axis of the frame attached to body I. Okay, so this is kinematics as we know. Now there will be, now dynamics comes in, somewhere there will be the center of mass of this link, and the center of mass will have a velocity which we denote as Vci, and to the center of mass we have applied the force due to gravity, and this force is simply mi, the mass of the link, times the acceleration vector in the direction, in the vertical direction. Of course, this body may change orientation, but the force always goes down to the center of the Earth. What else? Let's call Fi, and this will be a recursive notation, the forces that the link I minus 1 applies to link I through the joint I. And we consider this force applied to the origin of frame I minus 1. Similarly, Fi plus 1 will be the force that this body applies to the following link. And again, this force will be applied to the origin of frame I. Now, if we look at all this vector, velocities, acceleration, forces, everything should be expressed in the same frame. And in fact, we will use the local frame, so the concept of moving frames, to do this balance. So we will use reference frame I, although this equality holds for any desired, any chosen frame. So the Newton equation is as simple as that. The sum of all forces acting on the body, and these are three types. The force coming from the previous link, the opposite of the force transferred to the following link because of the principle of action and reaction, so there's a minus sign here, and the force applied due to gravity. So the sum of forces is equal to the variation of the linear momentum, which is nothing else than the product of the mass of this link, mi, times the acceleration of the center of mass, ACI. And this is, we have a pink field with an N, a capital N letter, which stands for Newton. This is the Newton equation that we will use. And you see that this is an equation that I wrote for the generic link, so I can repeat this equation as many times as are the number of link in motion, so n times, in fact. Okay, so let's move to the balance of torques, what we have friendly called the Euler part of the Newton-Euler equation. Okay, so we have a balance of torques equal to the variation of the angular momentum. Now let's see what are the torques acting on this body. So this is a free body diagram. And remember that there are pure torques transmitted or applied to a body. But in general, every time you have a force and you're considering a reference point, these forces typically, if its line of action does not pass through this point, will generate also what we call a torque, a momentum. Okay? So in doing this balance, we have to consider, as before, the pure torque transmitted from link I minus 1 to link I, which we called tau I, and the pure torque transmitted from link I to link I plus 1, which we call tau I plus 1. But of course, since the balance is made on link I, by the principle of action and reaction, we should consider this with a minus sign. So the torque transmitted from link I plus 1 to link I. But there are extra torques being produced by the forces acting on this system. And now we have to define some point with respect to which we express the resulting torques. We could use any point, but it is convenient to use at least one point where one of these forces vanishes. So passing, the line of action of this force is passing through this point. And here we have three possible choices. The common one will be the choice of the center of mass. Because if we consider the center of mass as the point through which we compute the effect of torques of on the body of forces applied to it, the gravity term will vanish because it's exactly, its line of action is passing exactly through the center of mass. Okay? So we have defined tau I plus 1. Now what is the torque produced by the force Fi transmitted from link I minus 1 to link I? It's just the vector product of Fi times the vector going from the origin of I minus 1 to the center of mass. So we call this our I minus 1 Ci. And similarly, the torque produced by the force minus Fi plus 1, so the force from link I plus 1 to link I on body I, when we are using Ci as the expressing point, will be minus Fi plus 1 because of the principle of action and reaction vector product, the vector going from the origin of frame I to the center of mass itself. Remember that this vector, RICI, will be constant if we express things in frame I. So if I have a body and I have a frame attached here, the vector going to the center of mass of this body in this frame will be constant, no matter if I'm changing the frame. But still, even if this is constant, when I'm writing derivative, this will be clearer later on, time derivative, because this is a vector expressed in a moving frame, the derivative will introduce some extra term. Not for this particular vector, but for a similar vector of constant length. So we have everything we need. I have attached also the angular velocity of the body. This pertains to the whole body, not to a special point, although this vector is typically represented at the center of mass. So, again, this is the motivation why we chose this point, because the gravity force gives no torques in this case, so we eliminated one of the three previous forces. And the Euler equation is longer, but quite clear. So we have the torque transmitted from link I-1 to link I, the torque transmitted from link I+1 to link I, so it's minus the one transmitted from link I to I+1, and then the contribution of the two torques generated by the forces, Fi cross product Ri-1 Ci, and then minus Fi+1, because again we are reversing through the principle of action and reaction this force as acting on the link I, vector Ri/Ci. And this is equal to the variation of the angular momentum. We have computed this for a generic body. Now we are writing this for the body I. So it's inertia matrix I times angular acceleration omega dot I, and then this cross product, which involves twice the angular velocity omega. Again, this yellow formula will be labeled by this violet block with a capital letter inside. E stands for Euler. Of course, you have guessed correctly. Okay. And again, we have the angular acceleration of body I. Now, in the two equations, we have acceleration quantity, the angular acceleration omega I, and the VCI dot, so the angular acceleration ACI of the center of mass. So if we want to use a recursive formalism with moving frame, we should be able, just like we did for the linear and angular velocity for the algorithm for computing recursively the kinetic energy of our system, of our manipulator, we should set up recursive equation also for that. So this is the moving frame algorithm, and we will call this forward recursion of the method, because we start from the base, just like we did for the kinetic energy computation, so velocity computation in the Lagrange method. So we start from the base. The base may have some initial value, some initial velocity or acceleration in this case, and then we transmit this through the following body, including the effect or the contribution of each joint. Okay, so we will do this exactly in the same way that we did for pure velocity. In fact, in the formula, you need the linear acceleration of the center of mass, you need the angular acceleration, but you also need the omega. So the recursion on the omega should still be there. So we will use in this, actually, I could have changed the notation, but this slide was like this. In this slide, as an exception, I would say, I'm using this shorthand notation. So wherever you will find a vector which has no superscript, this is implicitly says that we are expressing that vector in the same frame of the subscript. So, for instance, if I write omega I only, this will mean that omega I is expressed in frame I. Sometimes I will put explicitly the superscript. So let's see this recursion. We know that the recursion, I mean, at least for the kinetic energy computation, we made a recursion with an index sigma that was 0 or 1, depending on the fact that the robot joint was prismatic or not. So a sigma I for each joint. We could do the same here, but in fact, for simplicity, I'm just presenting the case of only revolute joints. So only the expression for revolute joints. In the textbook, you will find the full expression also in the case of prismatic joints. Okay, this is horrible, but this is what you compute. And pay attention, before entering into the detail, all these quantities will be evaluated numerically. So you don't have to carry over this long expression symbolically from one link to the other. This is the trick. So let's start with the first one. The first one is known. The first one is exactly the same recursion that we have for revolute joints in the kinetic energy computation. So omega I, in fact, this would be omega I superscript I, so expressed in frame I, is the omega I minus 1, so the angular velocity of the previous link expressed in its frame I minus 1, and I'm dropping the superscript, plus the contribution of the joint, which is a revolute joint in our assumption. So this contribution will be the intensity of the joint variable, so q I dot. If you wish, you could write here theta I dot, because this is a revolute joint. And this scalar is weights the unit direction of the joint, which is zi minus 1. And remember that zi minus 1 is expressed in I minus 1, so in fact is always 0, 0, 1. So this is something that we know, and then these quantities will be re-expressed in the frame I, so it will multiply by, let's say, Ri I minus 1, or which is the same, Ri minus 1 Ri transpose. Why we are using the transpose? Because Ri minus 1 I is exactly the rotation matrix that you find in the Denavit-Artenberg homogeneous transformation, so you don't have to do this reversal of index. So now we take the time derivative of this. And this will require some passages. Let's start with, so again, remember that we are in a moving frame, but let's look at this expression. So we have to take the time derivative of the left-hand side. This will be the angular acceleration of the body, so omega I dot. And then I have several terms here. So I have the rotation matrix, which changes in time. So it should be differentiated, in fact. And then the terms in the parentheses. So we do the distribution of the differentiation. So first, we don't take the derivative of the rotation matrix. So inside we have these two terms. So we have omega I minus 1 dot, and then here the rotation, the acceleration qi dot times the I minus 1. Now, you should take the derivative further, but if you remember that we are dealing with a rotation, with a moving, with a vector expressed in a moving frame, then there will be an extra contribution coming from here, because this is a unit vector. So it doesn't change intensity, but it rotates with the frame. So we know that it will generate also a cross product of the angular velocity that we are having, so omega I minus 1, vector, the cross vector, the same vector zi minus 1 here. And everything is pre-multiplied by qi dot. So this will be the derivation of this. Now you can directly use this expression, or do the computation more explicitly. And let's do this computation once for our purpose. So you could go directly to this final expression by using the formula that we have seen at the beginning, so derivation of a vector expressed in moving frame, or now analytically going through. So I'm rewriting here omega I, and for the purpose of clarity, now I'm using also the superscript, and then we will eliminate where this is not needed. So this is, again, our I minus 1 transpose, and then the term omega I minus 1 expressed in omega 1 dot plus qi double dot zi minus 1 expressed in I minus 1. And remember that this is simply 0, 0, 1. Okay. And then I have to, this is the internal derivation. And now I'm just considering that this is constant. But I have to differentiate also this. So now I have I minus 1 dot transpose. And this is multiplied by the previous expression, which is not differentiated, plus qi dot zi minus 1, I minus 1. Okay? Now, this is the extra term which will eventually build up this term. But let's see how this is done. First of all, again, you can consider that you take the time derivative of a transpose matrix, but these two operations can be exchanged. So I take the time derivative of the original rotation matrix, and then I transpose this. Very simple. So what do I get? So I'm expanding now only this term, so equal a certain number of things. Then plus, here I will have, again, skew-symmetric matrix of what? This is our I minus 1 I, so this will be omega I expressed in I minus 1 times R I minus 1, and everything will be transposed. And then times the same thing. Again, let's do some more computation. I'm bringing now the transposition inside. So I have R I minus 1 I transpose, and then I will have S transpose omega I minus 1. And then same story here. But this is a skew-symmetric, so its transpose is equal to minus this. So I will put the minus here, and I will cancel this. And moreover, what is the contribution here of this term? Let me check if I'm doing things correctly. Oh, yeah. What is this? This is just qi dot zi minus 1 expressed in I minus 1. Because this is the angular velocity that the body has because of the introduction of the joint. So now if we are putting everything together, I can factor out the rotation matrix transpose is here, and it's also here. And then I will have the first two terms coming from here above, which is omega I minus 1 expressed in I minus 1 with the dot. So it's an angular velocity, angular acceleration, sorry, plus qi double dot zi minus 1 in I minus 1. This is a constant vector. And now here, I'm reversing with the skew-symmetric term. I have a minus sign in front, so let's start with the minus. And then skew-symmetric matrix time whatever is inside here, this will be cross-vector product. So the first cross-vector product is omega I minus 1 cross-vector of omega I minus 1, I minus 1. Sorry. Yeah, yeah. So my notes were not correct, but anyway. So I'm using this. I'm using this expression here. So qi dot zi minus 1, I minus 1. And then again, minus qi dot zi minus 1, I minus 1, vector zi minus 1, I minus 1. Okay, so we have to close this. And now we recognize that this term is a cross vector of the same vector. So this vanishes. And now we exchange this, the order in this vector product. So we will get from here omega I minus 1, I minus 1 vector qi dot zi minus 1, I minus 1 with a plus sign, which cancel this minus sign. And now if we compare this expression with what we have here, we have found the first term. The second term is the acceleration qi dot zi minus 1. And then we have qi dot, which can be taken out, is a scalar from here, omega I minus 1 times zi minus 1. And now I can drop away all the superscript, and I obtain exactly this one. So I had I minus 1 here, I minus 1 here, I minus 1 here, and I minus 1 here. Now they are dropped in this formula. Okay, so sorry, this was kind of a complex. It's very simple to get confused with index, but this is what we have in this recursion. And similarly, we have a second formula. I will not give a proof, but you can try it by yourself, for the linear acceleration of the origin of frame I. And again, you start with the expression of the linear velocity expressed in local terms. Then you replace all the things. You have also a vector that generates a unit vector that generates this extra term, because this is expressed in this unit vector is expressed in, or this constant vector, better say, is expressed in the moving frame. And then you do the recursion. You introduce the rotation matrix where needed. So you bring up this quantity, which was defined in I minus 1. All these quantities will be defined already in frame I. And similarly, you have, finally, you get the acceleration of the center of mass from the acceleration of this other point. This is the second order version of the fundamental law of kinematic of rigid bodies. So the velocity of one point is the velocity of another point plus omega vector, cross vector, the vector of distance between the 2 points. When you take the derivative of this, you get this one. So that recursion again is made on omega, like in the Euler and in the Lagrange method, on omega dot, on AI. So this plays the take the place of recursion on omega I and VI. So omega I dot and AI, and then you move this to the acceleration of the center of mass, which you need in the Newton equation. So all this, it's called acceleration recursion. So there's a yellow box with 2 capital letters, AR, means acceleration recursion. And it's in the forward direction. Of course, you're doing also recursion of omega, but all is needed for the acceleration. Okay, now one very important thing. You have to initialize this recursion, just like we did with the moving frame for the kinetic energy. So you need an initialization for omega, so the angular velocity of body 0. typically this is 0. And for omega dot 0, so the angular acceleration of the base frame. Since if we are considering fixed base manipulators and not mounted on mobile bases, all these quantities will be 0. But the last initialization is also critical. So you could choose here an A0, so a linear acceleration. Again, this is 0 if you have a fixed base. But you can plug in here, in a very smart way, also the acceleration of gravity. This is a linear acceleration, in fact, acting on the center of mass, so you will introduce this inside AI, and this will move then to ACI. So why are you doing this? So it's like saying that instead of having the bodies feeling the acceleration from their own mass and gravity, you say that the initial body is accelerating in the opposite direction, so it's going up. And the effect on the bodies is exactly the same. So you introduce the gravity acceleration only once in the base initialization, and then this will be transferred to the following link, and you don't have to include in the balance of forces the gravity in that case. So you have two choices. Either you don't put this, and then in the equation of Newton, you will consider also the effect of the gravity acceleration, so the force mi g0, or you introduce g0 only once here, and then you forget about gravity. Okay, it's a very interesting property, which also can lead to the flexible use of the Newton-Euler method. For instance, if you want to exclude gravity from your computation, you just put this initialization here with g0 equals 0. And then gravity disappears from all the computation. Or if you want to include gravity, you put here the vector of gravity, of course expressed in the 0 frame. If the 0 frame has the z0 axis going up, this vector will be 0, 0, minus 9.81 meter per second square. Okay? So take this in account. I put the note here later on. So this was the forward recursion. Okay, the forward recursion, we will go from base 0, where we initialize things, to link 1, link 2, up to link n. So we end up, so now we know all the kinematic quantities of the single body constituting the manipulator. In particular, the angular velocity omega I, the angular acceleration omega I dot, and the linear acceleration ACI of the center of masses, for I going from 1 to n. Now we use the balance equation of Newton and Euler, balance of forces and torques. But we will use this by reorganizing terms so that we compute quantities from the last link backward to the base. So we start with the last equation. So from ni to ni minus 1. So we just isolate the force with the lowest index on one side as expressed as a force with a higher index, and then mass times acceleration. And if you didn't initialize gravity in frame 0, you have to consider now gravity in frame I, because we are using the moving frame. But this is eliminated if in the forward recursion we have set g0 as base linear acceleration. Okay? So this is the simplification. And similarly, for the Euler equation, so the balance of torques, we are isolating the lowest index torque, tau I, and we're bringing everything on the other side. And you see that on the other side, we will have all quantities that are known. Either they are kinematic quantities. So on top, we have ACI that have been computed in the forward kinematic acceleration recursion. Here we have omega and omega dot, and that's it. plus we have Fi, but Fi has been already computed in the previous equation, and Fi plus 1, and tau I plus 1, which are coming from the previous recursion that we initialized with I equal n. Okay? So nothing special, just isolating Fi and tau I. Remember that Fi is a three-dimensional vector, and tau I is also a three-dimensional vector. So all these recursion are on vector defined in 3D. Okay? Now, again, we have to initialize this. So the force recursion, these are called FTR, so F bar T, so recursion of forces and torques. You know, this is another label that we'll use when we write down the whole algorithm. So how do we initialize this? We need to initialize only the forces and torques exchanged with the body n plus 1. But the body n plus 1 is not there. This is the end of the robot. It's the end effector. So these are typically initialized to 0. Unless you would like to compute the torque needed to perform a motion in which you have contact with the environment at the level of the end effector. And you specify a desired exchange force and torques with the environment. Then you initialize those values at the given instant as Fn plus 1 and tau n plus 1. Otherwise, if the robot is in free motion, the initialization of these quantities will be 0. Okay? Now, you go this from n to the base frame, so you compute out to F1 and tau 1, so you have Fn, tau n, Fn minus 1, tau n minus 1, and so on, down to F1 and tau 1. Where are the torques producing motion? Well, this two three-dimensional vector, which can be organized in a six-dimensional vector, in fact, contain only in part the torque associated to the motion. Okay? So we have to do a projection. And the projection is made differently depending if at joint I we have a prismatic joint or a revolute joint. If we have a prismatic joint, the fact that we are transferring a torque does not produce any motion. Instead, the force component Fi, when we project this along the direction of the unit direction of the axis of joint I, so Zi minus 1, then we have exactly the force producing work on that prismatic joint. Pay attention, Fi, because of the moving frame concept, is defined in frame I, so this Ci minus 1 should be defined also in frame I, so it's not 0, 0, 1 in general, okay? So this for how do you generate the scalar Ui from the vector Fi, and similarly, if the joint is revolute, the scalar Ui is obtained not from the force, but from the torque, tau I, because the torque, if has a component along the axis, this will generate motion around that axis. So same story. Now, forget for a moment this is the end of the story. Now, this is the generation of the active forces, let's say those that needs to be produced by motors in order to give a certain motion to the joints. The motion of the joints was in the Qi dot and Qi double dot that we found on the equation of the forward recursion. Now, if you want to include non-conservative forces that dissipate energy, this is the right place to do. And you see that you do it locally at each joint. For instance, if you're including viscous friction, you have to add on this side, let's say eta I is the viscous coefficient friction, what we called in different slide as FVI, okay? So that you have it on this side, and then you bring it then to the other side. And the UI will be on the right-hand side of the equivalent Euler-Lagrange equation. So pay attention to the sign here. This is plus, and these are positive coefficients. Okay, so what do you do with the remaining component? It's not just picking a component, it's doing a projection. So you're taking a scalar, only a scalar for each joint out of 6 quantities. Well, the remaining part of these quantities are internal forces that are transmitted through the joint from one link to the other. And you can compute this. Actually, you have computed it already, so you can estimate the internal forces by the Newton method, by the residual part which is left after the projection of the relevant force or torque vector. Okay? So this is quite an interesting aspect. Okay. Now, a number of comments on that. As I said, all this recursive equation could be evaluated also in symbolic terms. So I've written them, and then I replace Fi and tau I in the following one in the same way as I replace the omega dot, and AC from one link to the next one. I could do the full forward recursion in symbolic form, plugging those to initialize the reverse recursion, and then end up with a projection and a symbolic expression. Okay? Well, this is not an easy thing to do. Not by your computer, needless to say, even less by hand. The chance that you will make an error is close to 100%. But this is not the way in which you use this equation. As I said, you evaluate each passage in numeric form. So you plug in the number wherever you have it. And in this number, you include also the dynamic parameter of the system. Pay attention. You are forced here to have a knowledge of all parameters of the links. Unless you customize your equation, if you want to use this program in a general form, giving the data in input, but not simplifying things for the specific robot, which is a very convenient way to do, then you need to provide, in principle, all expression of the dynamic parameter of each link. So the mass, the position of the center of mass, or if you want the standard parameters, so the product of the mass times the vector of locating the center of mass, and the inertia matrix of each link. Because otherwise, the system will fail to have data. And you don't know in advance which data will not be used, because if some of this data will not be used and you don't specify it, or you specify an arbitrary value, 0 or 10 to the 5th, no problem, because this data will never be used in the computation for that specific robot, and you have no problem. But you don't know this in advance. So in principle, you should provide all this information. And this is a critical point, because you know that you cannot identify those parameters in general. You can only identify dynamic coefficients, so combination, which are those that appear explicitly in the Euler-Lagrange form. Those other will be relevant probably for the internal forces, but not for the forces producing motion. This is a very important comment, so that it's not really written here in this slide, but it's something that people are starting to realize while doing identification. So the summary is that you need the full dynamic parameters if you want to use Newton-Euler's, not just the dynamic coefficient. So either the manufacturer or the CAD provide this to you, or you cannot use this system, in much the same way as you need those parameters when you're doing simulation with systems like VREP or Gazebo, which implicitly use the Newton-Euler recursion. So they need to define for each body those parameters, even if they are not going to use those parameters. So this is a critical point, how to extract from dynamic coefficient feasible set of the missing dynamic parameters in order to use Newton-Euler or simulation packages like VREP. Okay? So, but having said that, let's go back to the computation more conventional of dynamic model for motion. So what you do is you do the numerical approach, not the symbolic one. So you substitute numerical values at each step. And so from moving from one step to the other in the forward or in the reverse direction, you're just moving three-dimensional vector. The fact that you're moving from joint 1 to joint 2 to joint 7 to joint 45, the fact that you have a huge number of joints, each single step has a constant complexity. In fact, the whole computation has a complexity which grows linearly with the number of joints, which is the best you can have in an algorithm. Okay? So especially if the number of n is large, then you have to do this. And in fact, the nice thing is that if you do this, you have a general formulas. You don't have to specialize this for your particular robot, as opposed to the Lagrange method where you need to do the computation symbolically for the specific robot, and then later on you may plug in numbers. But first you have to derive the model. Here, you don't have to derive the model explicitly. You just use this tool for computation, numerically. And this is a powerful, very powerful result. Okay? So, how is this recursion organized? Here, for instance, if you want to do inverse dynamics. So if you want to, you have an input, a desired motion of the joints. This, of course, may come from some desired motion of the end effector through kinematic inversion and differential kinematic inversion, but we know now the story. So our inputs are just the motion of the joints, and you would like to compute the torque associated to this motion. So classical inverse dynamic problem. So here it is. The inputs to your algorithm are Q1, Q1 dot, and Q1 double dot. You need all of them at a given instant. This will be any instant of time, up to Qn, Qn dot, Qn double dot, which are the position, velocity, and acceleration of the last joint. These are the input. And then you do the forward recursion from top to the end, from body 0 to body n. Body 0 is just the initialization at the robot base. As we said, omega 0, omega 0, A0 minus G expressed in frame 0, if you wish, but this is a nice choice. The standard choice is 0 for omega 0, 0 for omega dot 0, 0 for A0, and you leave only as an initial acceleration the opposite of the acceleration of gravity for the base. And now you combine this and you use the acceleration forward recursion to compute omega 1 dot, and A1. And from A1, you compute also AC1, in fact, so the acceleration of the center of mass. And you go down this until you get to the end with omega n dot, AN, and from AN also ACN, so the acceleration of the center of mass of the last link. At every step, you're using the input of that particular joint. Okay? Once you're here, you move to the backward force torque recursion. You initialize this with the force torques exchanged with the environment at the end effector. If there's no force, you initialize this to 0, otherwise you put the right numbers. And then you use the Newton-Euler balance force and torques equation by isolating the lower index force and torque, and then you move down. And in doing this, you're using at every time the kinematic quantity that you have computed in the forward recursion. Okay? Once you have these vectors, this is a three-dimensional vector, and tau n is also a three-dimensional vector, up to F1 and tau 1, then you do the projection, generalized force projection. So you pick either Fn, either Fi or tau I, depending on the nature of joint I. If it's prismatic, you pick up Fi. If it's revolute, you pick up tau I, and you project on the axis of that joint, and you obtain U1, UN. So the torques at that particular instance. So this is an algorithm that can be used anytime, not necessarily at scale time, so every 1 millisecond, but of course this is the usual way of doing things. At any instant of time, you just plug in the inputs, and you get, at that time, the outputs, which are the generalized torques, producing that type of motion. So in a state q dot, and with a desired acceleration q double dot. So this is reminded in that top block. Numeric step at every instance of time. Any, I would say. Anywhere, anytime. So, with this in mind, you can certainly build your own Newton-Euler recursion. I have one for myself, but you can build yours in any language, Matlab, C, Java, whatever you wish. And the program is generic. So you have to specify some input which relates to the number of joints, the type of joint, the dynamic parameters of the links, the dynamic Hartenberg parameters in such a way that you compute the rotation matrices and so on. So this is the data set for a specific robot. And then with this in mind, you call this routine, and you call this routine with, let's say, 4 arguments in general. One of these arguments is not so relevant, so I use it as a subscript for the definition. This algorithm is called NE, so Newton-Euler, and the output will be something useful. But if you have this in mind, you can call this algorithm with different inputs, argument, and also subscript alpha, and generate different things. So the data file, again, is the number n of link, the type, so a vector of sigmas, 0, 1, depending on the revolute or prismatic joint, the table of DH parameter, and the list of dynamic parameters of the links. And if you have also the motors, you add also the motors to this. In the textbook, you have the full recursion, including the motor. I think that the notation becomes very heavy in that case, but there's nothing special. You have just to assign frames also to the motors as rigid bodies, and do the recursion, including the motors in the picture. So the input, the vector, the parameter alpha, is just on-off. If you put 0, you're assuming that you're not in gravity. So it's like initializing the G0, so the gravity acceleration of the base, at the 0, 0, 0 value. Or you put G0, meaning that you have some gravity acceleration, or just a fraction if you're moving on an inclined plane, whatever. Okay. So essentially, if you put the G0, you are in presence of gravity, full presence of gravity, and if you put 0, you don't have gravity. And then you have 3 ordered vector arguments. Now this vector argument, pay attention, typically are position, velocity, and acceleration, the inputs in the previous inverse dynamics computation. But you may play around with this argument and generate nice things. So typically are taken from a desired trajectory, but not necessarily. So the output could be, in fact, the inverse dynamics in the complete form, or really single terms or special quantities from the dynamics. And let's do some examples. This is very nice, I guess. I mean, I like it very much. So first example is the trivial one, the one known basically in literature. So you call the Newton-Euler routine, including gravity, if gravity is present, and specifying a value for q as q desired, q dot as q desired dot, and q double dot desired. So what you generate is a vector of numbers, ud, which are associated to this value at the given instant of time. You don't care which instant it is. And this UD is a vector of n component. N is the number of joints, which represent the evaluation of the full model on the desired state and acceleration. So mqd times q double dot desired plus c of qd q dot desired plus g of qd, and if you have included also friction, whatever friction model is there. Okay? So it's a computation of the inverse dynamics using an algorithm which has a linear complexity in the number n, which is tremendously more efficient than generating the full model in Lagrange form and then evaluating all these terms. Remember that the single terms in the model grows at an exponential rate in terms of number of terms to be evaluated. Okay? And then you have to derive them first symbolically, and only then you can plug in numbers. While here, you bypass completely this step. Okay? But you know that the output that you get is exactly the solution of the inverse dynamic problem, provided that you have put the right number inside. Okay, but this is a different story. But this is not the whole thing. So you can also, for instance, generate only the gravity terms. What do we mean by that? So I would like only to generate G, the last vector G, at the given configuration, a generic one, desired or not, Q, G of Q. How do I do this? Well, it's very easy. As a subscript, I should include the gravity, otherwise this would give 0. And the first input will be the configuration at which I would like to evaluate the gravity vector. And then I put 0, 0. 0 is, the second term is velocities. So 0 velocity means that the Coriolis and centrifugal term vanish. And 0 acceleration means that also the inertial term vanishes. So what remains is just G of Q evaluated at this value of Q. Very simple. Okay? So you can play around with the inputs also to extract some information at any desired configuration Q. Similarly, you can take out only the vector C of Q dot for any desired configuration with any desired value of Q dot. How do you do this? You call the Newton-Euler algorithm with a 0, which means that you will cancel out, you will not create G of Q inside the output, and with a 0 acceleration, which means that you're zeroing out also the inertial term. So in the given configuration Q and with a desired Q dot, you will generate only C of Q dot. Okay? Very nice. Well, you can play around even more sophisticated. For instance, you can generate in one run of the Newton-Euler algorithm a generic column of the inertia matrix. How do you do this? I think just a moment on this. Well, of course, you have to eliminate gravity. So I expect that I will put a 0 here. And I have to eliminate also Coriolis and centrifugal terms. So the second argument will be 0. I have to put some Q inside. But in fact, this is not enough. So I will put Q because I want to evaluate the inertia matrix at some configuration. But I use as acceleration just the unit vector with a 1 on position I and zeros on the other, which means that I'm extracting in this product M times EI only the ith column of the matrix, evaluated at Q. And if I want to evaluate the whole matrix in this way, I need to call n times the algorithm. And so I have the full M of Q numerically, not symbolically, but numerically as output of my routine called n times, with I going from 1 to n. Something cannot be computed nonetheless. For instance, if you want to compute a factorization or the element of a factorization of the Coriolis and centrifugal term, in particular, you would like to compute, let's say, the columns. Remember, the output of this program are always column vectors. So suppose now that you have C of Q dot, and you would like to have a factorization S of Q dot, and you would like to compute, let's say, the columns Si of this matrix. Okay. Now, if you call, I put a question mark here. If you call this with 0 subscript so that you eliminate gravity, and you certainly have to call this at the configuration Q, because Q is here inside, you would like to eliminate acceleration, so the inertial term is gone, the gravity term is gone. I'm focusing now on this. And if you put here EI, or even QI dot EI, then you may take a column of this, but in fact, you're taking a column, but you're using the wrong velocity inside this matrix. You will find the matrix evaluated at this specific velocity vector, which has only one scalar component there. So to make a long story short, you cannot use this algorithm for doing this, in the same way that you cannot use this algorithm for computing a quantity which will be relevant for some control law, which is the following one. The Coriolis and centrifugal terms evaluated using the factorization S, but inside the S you're using the actual velocity, outside the S you're using the desired velocity. Now this algorithm is not able to discriminate the two. You need a generalized version of the Newton-Euler algorithm, which takes 4 inputs into account. And the first input is a position, second and third input are 2 velocities, and last input is an acceleration. And if the 2 velocities at the second and third input argument of this function are the same velocity, you will generate C of Q dot. But if they are different, you can generate something like that. Okay? We developed this in a paper a few years ago, so if you're interested, I can provide you the reference for that. The last example that I would like to treat is the following one. With the same algorithm, we can generate also the generalized momentum. And this is interesting because the generalized momentum is a quantity that can be used also for some operative condition. For instance, we proposed a very successful collision detection algorithm which monitors the evolution of the generalized momentum of our robot without using extra sensor. And from there, we can detect a collision and possibly also isolate this. So what is the generalized momentum? Is simply, I remind you, we would like to generate as output of this system, a vector P, which is just mq times q dot. This is the generalized momentum of the robot, the product of the inertia matrix times the velocity. And this vector can be generated in a very nice way by calling this algorithm in this way. So putting 0 as a subscript, so eliminating the gravity. Indeed, having q here, because we are evaluating this at the given configuration, we put 0 on the so-called, the second argument, the so-called velocity, although we have a velocity here. But this velocity does not appear in the Coriolis and centrifugal term, but takes the place of the acceleration in the inertial term. So we place q dot as a third argument. So instead of generating mq times q double dot, we generate mq times q dot. We know for sure that this is the output of our system. Okay, and the output has been labeled as U, just because of U is the generic output for the inverse dynamics. But this is just the output of our algorithm. Okay, so you can apply this in nice ways. Okay, so let me make a simple example. I'm taking the 2R planar robot, and I'm doing a motion which is, I would say, a rest-to-rest motion, yes, in fact, between the folded configuration. So this is the arm straight and folded completely. So it goes up and down, link length are 1, so you just see the two links superposed. From this, then you want to open the structure and obtain a configuration like this. So you're going from 90 degrees, well, 0 degrees is the horizontal, so 90 degrees for the first joint, and then you fold it by 180, minus 180 degrees to a configuration which is 0, so horizontal for the first link, and 90 for the second link. Okay? And you see there a stroboscopic view of the evaluation. And you're using a quintic polynomial for doing this motion in a finite time, in a given time, that's 1 second. So quintic polynomial allows you to specify for each joint the initial value, the final value, the initial velocity, the final velocity, and also initial and final acceleration, which we set all to 0. And this will be the quintic rest-to-rest polynomial for joint 1. You see that it goes from 90 degrees to 0, and the velocity goes from 0 to 0, and same for the acceleration. The acceleration, remember, you have a quintic polynomial for the position, so you have a quartic polynomial for the velocity, and you have a cubic polynomial for the acceleration. In fact, you see that it's a smooth one. You have a symmetry with respect to the half time. 1 second is the total time. And same for the second joint. Now we are moving from minus 180 to 0, and then from 0 to 0 for the velocity, and same story for the acceleration. And you can see from the scale that you get quite large value of velocity and acceleration, especially at the midpoint for the velocity. You get up to 200 degrees per second, which is quite high, and even larger for the acceleration in the 2 points where you have a maximum and minimum. But this is the desired motion. So I'm taking out of this desired trajectory samples of q, q dot, and q double dot for both joints, and I feed them into the Newton-Euler algorithm. Okay, and because of what we have seen, we can also call it the algorithm by pieces, so that we can generate the individual term g of q, c of q, q dot, and by difference also m of q, q double dot. Okay, if we call them the whole algorithm. So, for instance, this is the full inverse dynamics. The motion occurs in the vertical plane, so I'm calling the algorithm in full with n of g0 and e of g0 times q desired, with arguments q desired, q dot desired, and q double dot desired. I'm specifying some data. In particular here, I'm assuming that these are thin rods of uniform masses, 10 kilograms and 5 kilograms. This implies also some expression of the inertia. I know that only parts of this dynamic parameters are being used, in particular only the inertia around axes which are normal to the plane of motion for each links. So we know everything from the Euler-Lagrange approach, we know everything about this. Okay, but if we want to use, in this case, the Newton-Euler, we have to plug in numbers, or don't care numbers, if we know in advance that these numbers will not appear in the actual computation, or arbitrary values. Okay, so at the end, we get these two profile of torques. Good or bad, we don't care. We just check that things are fine, that we didn't make any mistake. For instance, at the initial point, the torque is 0. Why? Because I'm starting with 0 acceleration, 0 velocity, And this configuration, straight up and folded, is an equilibrium configuration where g of q is 0. So I don't need any torque to stay there. Okay? And then I'm moving at the end, at the final torques, the final configuration will be this one. Again, 0 velocity at the end, 0 acceleration at the end. So the only thing that remains is the gravity. And I need a torque, actually a positive torque, so going counterclockwise to hold the first link, while I don't need any torque to sustain this second link in equilibrium. In fact, the final value of this torque is 0. The final torque for the first joint is positive, and by the way, is also about 100 Newton meter. The total weight, the weight of the first joint is, let me see if this has a meaning. Well, sure. I have to take into account the link length and so on to get the value of this, but essentially this is the result of 10 kilograms. Okay. Now, indeed, I can also call the algorithm in parts, so I can see the total torque, the red curve, how it is built from the different contribution. And you may recognize in the slide the dashed violet one is the one due to gravity. This is the component that will not scale if now I'm doing the motion in 2 seconds or in half a second or in 20 seconds. These values will be assumed during the motion because they are only configuration dependent. The dashed blue part instead is the inertial one with the acceleration. And in fact, you see that it goes to 0 at the end for both joints because at the end and at the beginning and at the end of the trajectory, we start and end with 0 acceleration, so the inertial contribution is 0. And Coriolis and centrifugal force are the dashed dot green line. And again, also this profile goes to 0 at the beginning and at the end because we start and end with 0 velocity. But during motion, the 3 dashed or dotted lines will add up to generate the total torque. And you can see that there's a large phase, for instance, for joint 2, in which most of the torque is given by the inertial contribution. Because the acceleration grows and then covers most of this effect. In the first few instants of time, velocity is low, gravity is almost 0 in that configuration, so everything is given by the presence of an acceleration, and so on. So you can argue about the composition of your total torque. Now, to be honest, of course, this analysis could have been done, especially for the 2R planar robot, even without the use of the Newton-Euler algorithm. Just building up the Euler-Lagrange method and then evaluating separately m of q times q double dots desired, c of q, q dots desired, and g of q desired, and then adding all them together. And the result would be exactly the same. But the power of the Newton-Euler method is that you can do this also for a 7-jointed robot, and guess what? You will take quite a long time to generate a correct model for the 7R, let's say, KUKA lightweight robot. While here, you just do this computation with the same program once for all by inputting the data of that robot and inputting the data of the desired trajectory. Last thing. So the main use of Newton-Euler in the literature, at least, is for inverse dynamics. But you can use this also for direct dynamics. Why? Because you can, again, you don't need to derive the full symbolic model. and still you can compute whatever you need. So what is the direct dynamics? Now we are not assigning a desired motion, we are given an input, and we would like to integrate this differential equation. Now you can do this with your own routine, you can use Simulink for doing that, but no matter what you do, at some point you have to evaluate the dynamic terms. Which terms and how? So from the model, let's make it compact. So I have m of q double dot equal plus c plus g equal u. Now I'm isolating the acceleration because this is what I need to integrate once and twice to get the next velocity and next position at discrete instant of time. So I'm isolating the acceleration, so I have m of minus 1 of q times u, the input that I would like to apply, and I can choose any input torque. That could be a predefined torque profile or a torque generated by some feedback law depending on the state. I don't care, just inputting that torque. So I group C and G as a single vector n just for compactness. So I have to compute those terms. So I have to compute the inertia matrix and its inverse, and the sum of Coriolis and centrifugal and gravity term. At every state q dot, and then I add also the input torque. So I can call once the Newton-Euler algorithm with the subscript G0 so that I compute, if present, also the gravity terms, and calling this for q and q dot and 0 for the acceleration. So I discard the inertial part, so I'm computing exactly c plus g, or with a compact term n. And this is one call at every instant of integration. Then I have to generate the inertia matrix and its inverse. We have seen that we can do this by generating the column of the inertia matrix. So I'm calling n times the Newton-Euler algorithm with a 0 here, so that gravity is gone, with the 0 in velocity so that Coriolis and centrifugal terms are gone, at the current configuration q, and with the unit vector 0, 0, 1 in position I, 0, to select the ith column numerically. I'm obtaining the numerical version of the ith column at the current configuration q. And I do this n times, so I generate the whole matrix. And now I have a matrix of numbers. Let's say a 6 by 6 matrix for a 6-dimensional, 6 degree of freedom robot, a 7 by 7 for the KUKA lightweight robot, which has 7 revolute joints. So I take this matrix of numbers and I call the inversion routine of Matlab. I'm writing this in Matlab, but this would be, which is not terrible. Okay, so I'm calling this inv m, and then this will be used to pre-multiply u minus n, okay, and to generate the acceleration, which will be integrated. So if you're doing a block diagram in Simulink, you will call these blocks, one that evaluates through Newton-Euler the n vector, ones that evaluates all the columns of the inertia matrix and does the inversion, and then you do this product. And you're done, in the sense that now you can pass this acceleration to the routine of integration that you're using from the menu, let's say Adams-Bashford or Runge-Kutta method of the fourth order and so on. So you generate the new state and then you repeat over time. Very simple. So what is the complexity of this algorithm now? Well, you have linear complexity for generating n in terms of the number of joints. You're calling n times, again, the algorithm for generating the columns of the inertia matrix. So this has a complexity n squared because every iteration has a complexity n, so there are n iterations. And then the inversion of a numerical method has a complexity that grows, let's say, with n cubed, but n is not so large, or anyway, it's n cubed, but the coefficient in front of this n cube is very small. So this is the asymptotic complexity. So essentially, while the whole method is n cube of complexity, but in fact, the dominant part is n squared. And this is very efficient for n even quite large. Okay? And again, don't forget that the advantage is that you're not deriving the model explicitly and then evaluating the symbolic terms. You're just computing numbers. Okay? So you never see anything nice like you write on paper for dynamic models with the Euler-Lagrange approach. Okay, this is the end of this part, and from now on, the next lecture, whenever it will be, we will start talking about motion control for robot manipulators. Thank you.